Chatterjee, did I pronounce correctly? Chatterjee, sorry, yeah, from the City University of New York, talking about the effect of restrictive interactions on epidemics.
Thank you. Thanks for the invitation to present my work here. I'm thankful to NSF for supporting my research. So my research is in the area of probability and statistics and mathematical modeling. So my thesis was in the area of epidemic models, particularly SIS epidemic models. So after that, I have been thinking of how to address the question that if there are restrictions to block infection passages in different ways, how does it affect the regular infection models like SIS or SIR? So, and then whether we can have some sort of causal inference based associations or attributions that this is the cause, certain things are cause of certain things, etc. So I have in this talk, I'll talk about two different perspectives from two different angles. One is a rigorous mathematical analysis of a particular mathematical model, which is a variant of the contact process or SIS epidemic model, where restrictions are there. And the other one is sort of more exploratory, that is ongoing right now. So that is from a bird's eye view, what kind of restriction we can impose in the outbreak of a pandemic, and what are the concerns if we can throw all of them, or at least most of them in the bucket, how does the model look like, and what are the things to aim at. So that is the second part. Third part I wanted to, but probably I'll not have time. So that's the observational causal inference to establish or not establish whether certain measures like masking measure or putting people at home, shelter at home measures, they're actually effective. Can we say from the causal inference point of view in statistics? But that will be a different talk. I can talk offline if you're interested. Okay, so the first part is a joint work with David Sivakov and Matthew Washer from Ohio State. So yeah. Yeah. And we are still working in other areas. So
that's right.
Yeah. So so this is the short overview is that we first talk about what the contact process is, just to make sure probably all of you already know it, but just to make sure that everyone knows exactly what I'm talking about. Then I'll introduce a model which we'll be studying rigorously. It's called the contact process with avoidance. I'll make it clear what avoidance means. And then our results are very modest because there are a lot of less techniques available. So you have to invent techniques as well as you go. So we have results for Z, the one-dimensional line, cycles, which are cycle graphs, and star graphs, which are hubs. So those are the three places where we will compare the results with the regular contact process and see how it results. Okay, so the contact process or the SIS epidemic model is a particle system where it's like a flu infection, which is a recurring infection model, where every vertex has two possible states, I or S, infected or susceptible. So infection state, this is a Markovian process. So, like many other models, it has many limitations, but it has been classically introduced as a model for recurring infection, and it has attracted a lot of researchers in mathematics, in physics, and other areas for research. So the dynamics goes as follows: that we use psi at to denote the process starting from an initial set A at time t. And then this is a continuous time Markov process. Each vertex has two possible states, as I said. You can say 0 or 1. 1 means infected, 0 means susceptible. So from one state, a vertex goes to 0 state after a fixed mean amount of time. The distribution is exponential, but you can always normalize time to make it have mean 1 in this case. So then this is left with only one parameter lambda, which is the infection rate across each edge. So each edge passes the infection to the neighbor at rate lambda. So lambda is the only parameter here. So pictorially, if you start with an infection, one vertex, then it can, try to infect its neighbors at rate lambda, and so on. And then it also, the infected vertices can get healed at rate 1. So there's a competition between those two phenomena. Like this. This is just an example.
N of V means a set of neighbors of V?
Yes. So each edge has infection rate lambda. So that's why if we compute the rate at which a particular vertex gets infected, it's lambda times the number of neighbors of it.
And are you assuming anything about the degree distribution?
No, it's just on the, just on this line so far. Yeah, I'll come to the degree distribution soon.
So it's not a random graph, it's just some kind of structure.
Yeah. Okay, so the main mathematical tool for studying this kind of processes is called the Harris construction, which was introduced by Harris, or graphical representation, where the space is in the x-axis and time goes up in the vertical axis. And for each element of the space, in the time axis, we draw dots from Poisson process at rate 1, which corresponds to the recovery dots. And the arrows are also for each pair of vertices. There's an arrow. The arrows are also followed by another independent Poisson process with rate lambda. So the arrows means that the infection trail follows the arrow from tail to head. That's why there is arrow. So that is sort of the, in some sense, the probability space, or in some sense, the basic structure on which the process can be defined. So these Poisson processes, they're independent. They're independent for each pairs of edges and for each vertex. So each vertex has a recovery Poisson process, and each edge has the infection and Poisson processes. So the edges can be considered as directed or undirected. In this case, will not have any difference. Now, once such a construction is there, then we can define the whole process, the contact process, starting from any configuration of zeros and ones below. So namely, you start from, suppose you have a particular configuration of zeros and one. Remember, 0 represents susceptible, 1 is infected. So now starting from any set of ones, we try to go up, follow the arrows to branch out, but we are not allowed to cross any recovery dot. And if we fix a time here, and the set of, at this time, whatever vertices you get as ones, which you can reach from below, following these arrows and without going across any recovery dot, will be 1 at that time, will be infected at that time. So that helps us to construct or couple contact processes starting from different initial conditions all at once. One of the important properties of this contact process, there are many others. So one of the important properties that I'm going to contrast with the avoidance process and going to be crucial is the monotonicity property. So it is monotone in two senses, that if you have higher infections initially, that will then the distribution, stochastically you have the same or higher number of infections later. So more infections initially will correspond to more infections later in case of the contact process. Another monotonicity is the infection. If you have two different infection rates, one is smaller than the other, then the process corresponding to the higher infection rate will have higher number of infected vertices at later times. So these are all in terms of distributions, but this can be established using the graphical constructions. So basically, if you have more arrows, that means if you have more infections, the infection rate is higher, then you'll reach more vertices at the top, higher level at later time t, starting from the same initial at time 0. On the other hand, also if you have more ones in the bottom, then you'll reach out to more people. So that is straightforward in this case. Like for example, if this particular status, vertex status was 0 here, that's why that becomes 0. But if we had another configuration was 1 here, and that was the reason the neighbor was 1 at that time. Now, the critical value. So one of the important mathematical objects for studying in these cases where things are monotone is the critical value, where the behavior of the process changes. So in case of contact process, and infinite graphs, either ZD or homogeneous tree, etc., infinite graphs, the critical value can be defined as the smallest value of lambda for which you have the infection stays on forever with positive probability. Or equivalently, largest value of lambda for which the infection does not stay on with probability 1, starting from finite state. Now, classically, a lot of study was there to establish that lambda C is non-trivial, lambda C is positive, and whether the two, whether there are multiple critical values in terms of different kinds of continuation of the infection and so on. So it turns out that in case of straight line, the lambda C is positive, and approximate values from simulations and other numerical considerations is approximately 1.65 around that value. The exact value is it's not a closed form solution. Now, it turns out when we concentrate on finite graphs instead of infinite graphs, then the notion of the critical value is slightly different, because in case of finite graphs, what happens, the process eventually dies out. The infection dies out. It means infection, everyone becomes healthy eventually. So it's a Markov process with an absorbing state. So the same way we cannot define the critical value. In this case, we look at the value, the time of extinction time, the order of that. So if the extinction time is long, then we consider that to be a supercritical. And if the extinction time is small, that we consider to be subcritical. Now, what is long, what is small depends on the context. From model to model, it varies. So it turns out in these cases of contact processes on finite graph, long corresponds to exponential or stretched exponential persistence of the infection, and short corresponds to logarithmic or polylogarithmic persistence of the infection.
Is the lambda C unique, or can there be two different lambda C's?
So if you define lambda C to be the way I define, that's unique. But in case of homogeneous trees, there are two different lambda C's, because depending on the kind of survival. There's a survival called strong survival, where a particular vertex keeps on getting infected, infinitely often. And the weak survival is where the infection stays somewhere in the graph. So those two are different in case of homogeneous trees, but not in case of lattices or lattices.
Oh, it's for lattices. Okay.
Yeah, thanks. For example, if you consider cycles that are torus or this kind of finite graphs, it is well known that when lambda is bigger than same lambda C critical, then the survival time is exponential, of the order of exponential. Like for example, the expected value of the survival time is exponential in the size of the graph. And when lambda is less than lambda C, it is logarithmic. That is there. Now the question was that next, after studying the contact process on infinite graphs and finite versions of the infinite graphs, like torus and cycles, people looked at random graphs. Now, there are different ways to construct random graphs. One is a few of them which got very popular, the preferential attachment kind of models, where you have a sequence of growing graphs where vertices come in and attach to the existing vertices with some rules proportional to the existing degrees or some function of that. That's a preferential attachment model. There's also configuration model, which where people choose a distribution first, and then choose the degrees from the distribution, d1, d2, dn, degrees for n vertices. Subject to that, the sum is constrained to the sum is even, so that you have a valid graph. And then you do a random matching of the half edges. You can assign the di many half edges to vertex I and do random matching. That's how we construct the random graph. The idea is to have a uniformly chosen graph from all collection of graphs having the same proportional degree. But there are some variants of this also. This is not the only way of constructing. Now the next question was, the social networks resemble this kind of graphs. So people are interested in how does the contact process behave in these kind of social networks or internet networks. So there are different approaches. In 2001 and 2, around the time, people used mean-field calculations for studying both SIR epidemic and SIS epidemic models. For SIR epidemic models, they found that it has a non-trivial phase transition, the mean-field calculation, and it was like a percolation model on the graphs. For SIS model also, the result was that if you follow mean-field kind of approach, then depending on the degree distribution exponents, there are phase transitions, or there may not be any phase transition depending on what the exponent gamma is. When gamma is small, there is no phase transition according to the mean-field calculation, and then when gamma is large, there is. 2005, Christian was one of the authors, and there are 3 other authors, Berger, Chase, and Saberi. They first showed that differential attachment model, which corresponds to gamma equal to 3, has no critical value for the contact process. That means whatever lambda you choose, the process can survive for a long time. So the main reason of the argument was the behavior on the star graph, which I'm going to talk about later also, that the process sort of, the star graph sort of act as a reservoir for the infection. And that's enough to show that, and then since the contact process is attractive in the sense they have a monotonicity property, if a particular subset acts as a reservoir, it's a reservoir for the whole graph. Because if there are more infections, the infections can die down. Later on in my thesis, I showed with Professor Duret that not only on gamma equal to 3, it's true for any gamma bigger than 2, and the exponential the persistence is almost exponential.
So the physicists are wrong.
Yes, in this case, I mean, mean-field calculation is wrong. Let me put it that way. So.
The comment was made that the physicists were wrong, and I've seen Rick talk about this, and he was quite proud of the fact that it's always satisfactory for a mathematician to show the physicists that they're wrong.
Okay, only thing I can say is that if we look at the metastable density, the metastable density is like a lambda to the power some power which grows with alpha. So when alpha is large, it's like a power which sort of goes to 0 very slowly. So if we do simulation, it's very difficult to capture that is positive or almost 0. Yeah, so. Okay, so and then people have also looked at, but there are other cases where the mean-field calculation is actually right. Like for example, Peterson looked at complete graph with random weights. In that case, indeed, the contact process has a non-trivial destination. Okay, so now next question was, can we have exponential? There is the maximum amount of persistence that's possible in these kind of models. So it was established for configuration models by first it was we showed the result that is almost exponential but not exactly exponential. So first it was improved by Mountford, Vallesin, and Yao to show that this is exactly exponential. Then other people have worked on preferential attachment models, and then other power law graphs with exponent smaller than 2, because I work with exponent bigger than 2. So recently, there have been also studies where people consider dynamic versions of the graph, in particular dynamics, where the dynamics is so fast that it mixes very quickly. So then when the exponent gamma is bigger than 4, exponential persistence is possible to show, and there's a phase transition there. Lambda c is positive. Very recently, Shankar Vamidi, Alan Sly, and some others, their students and colleagues, have shown that the degree distribution has a role to play in determining whether there is a phase transition or not. In particular, if the degree distribution has an exponential moment, that's an if and only if a necessary and sufficient condition for having lambda c positive or not. So lambda c is positive if and only if the degree distribution has exponential moments. If it doesn't, then it doesn't.
This is for configuration models.
Yes. No, there are subtle differences in these two critical values in this case. And this is only for the lambda 1, the smaller critical value for the trees.
So this means any power law.
So in particular, this doesn't just mean gamma bigger than 3 or 2. It means any power law will have lambda c equals 0.
Right. Yeah. That was already shown before. That my result showed it for gamma bigger than 2. For gamma less than 2, there was a Khan, I think, was but this was a more stronger version of the result, saying that that's the finding the necessary and sufficient condition for existence of phase transition, this exponential moments. Okay, so now I come back to the avoidance question. Now, suppose I decide to avoid my friend if I find out that my friend is infected temporarily until my friend gets healthy. So then how does it change the dynamics? That's the main crux of the question. So here, only SI combinations have this extra addition, like avoidance. So there's a parameter alpha to it. So if I choose to, if I get to avoid before the infection is sent to me, then the infection is not sent to me, at least for that particular period. So that we can think about that there's an intuition. Intuitively, it should reduce the infection in the whole process, and or in terms of critical values, it should increase the critical value. So now let's see what happens. So this is a pictorial, and this was initially introduced in the physics literature. I think it has been in multiple papers there. Now there is no only one way to decide which model to choose, because you can avoid, but then when do you come back? When you reestablish the contact, there's no one way. Like you can wait for a random amount of time and then again reestablish the contact, or you can wait till you yourself become healthy, so that you don't want to go to your friend when you're infected, etc. There are different variants of this. So different papers have addressed this direction, different variants empirically.
So you're avoiding a friend who is infectious, who you know has symptoms, or how do you know if the friend is infected today? You wouldn't know that.
I don't know that. So that's why there's a competition between the infection and the avoidance. So if I get to know before the infection is passed to me, then only I can avoid. Otherwise not. Otherwise the infection will come to me anyway.
Okay.
So I'm not instantaneously, I'm getting the knowledge that my friend is infected. Only when sort of based on symptoms or other information or friend telling me or something, it's like my attempt to stay away from infected friends. Basically, it's individual attempt. It's not that someone government is announcing that these people are infected, not like that. So it's like individual level attempts.
Was D a probability or rate?
Alpha is a problem, rate, like lambda. It's
You
exponential.
just have a D and an A, one alpha.
Oh, sorry. Yeah, so I should. So D means deactivation and A means activation of the edges. So when I say
So D and A means deactivation, activation,
Right.
and at what rate do they happen?
so deactivation happens at rate alpha, and so then these papers have different versions. That's why I want to clarify the activation. Some papers have considered activation rates as separate parameter, beta, for example. But some authors have said that activation will be automatic when people both are healthy. Some people say that one of them is healthy. So there are different versions of that. So the deactivation, there is one parameter. So in the next slide, I'll specify which particular model we have results on. So we have deactivation rate alpha, one parameter. Activation, we don't have any other parameter.
Exponential time.
Yeah.
So this is still Markovian,
Still
right?
Markovian.
With these two. Okay.
Now, if you get the age gets deactivated, then I does not pass on the infection to S. So I becomes S on its own if there's no other, there's no other influence, then I becomes on its own healthy and stay there. This is called temporary deactivation. Now, this is the model that we studied rigorously, where, as I said, that alpha is the rate at which deactivation occurs. So now the contact process was only on the vertices. Now we have to consider both vertices and edges. So vertices are 1, 0. 1 means infected, 0 means susceptible or healthy. For edges, 1 means activated, 0 means deactivated. And then the dynamics are sort of, it's a mixed dynamics, it influences each other. So the vertex dynamics is similar, that once a vertex gets infected, the rate at which it gets healthy is rate 1. You can normalize time so that you have that. And then infection across each edge is lambda, like before. And then the alpha is a new parameter, which is the avoidance rate. So if alpha is very large, then you are quickly recognizing that your friend is infected. You'll be safer. Yeah. Okay, so is the model clear? Any question?
It's okay.
Okay, now this is the graphical construction. So we need more ingredients to represent the model. Initially, we just needed the recovery dots and the arrows, but we need a blocked arrows, and also we need a region which is sort of avoided regions. So blocked arrow means that that corresponds to the Poisson process with rate alpha. So again, recovery dots were for each vertex, vertical line has recovery dots Poisson process rate 1. Now we consider only directed graphs because who is blocking whom is important. So we consider directed graphs, and for each directed edge, I have a Poisson process lambda where the infection goes from tail to head. And then for each pair, ordered pair WV of neighbors, if there is a blocked arrow, that means that if W was infected, V was healthy, V is blocking the infection to come to V from W. So infection is blocked from tail to head again. And once the infection is blocked, then we stay until the infected person is getting healthy. And instantaneously, the block is removed. So in the graphical construction, all the infection arrows that falls between between a blocked arrow and a recovery dot is sort of ignored while constructing the process.
So you immediately get healthy after. So
You get immediately unblocked when you get healthy?
Yeah, that version we have studied. It's not the only version, as I said, but that's the version we studied. There can be another parameter also that you can use that, but that will make the model more complicated. So that's right. So as long as the infected person, as soon as the infected person is healthy, the infection is the block is removed. Okay, so the main difficulty, as I was saying, is that lack of monotonicity property. In this case, like for example, here is an instance of the same sort of structures in terms of arrows and dots. But in the left-hand side, you just have one infection, so infected individual at time 0, and the right-hand side I have 2. But at time t, at a later time, we have more infections here than there. Why is that? So the infection, this is just an instances. There are many ways it can behave like that. So the infection starting from here, it travels in these arrows and goes to here and then comes back. And so that's why you have these two vertices infected at this time, because you have an infection trail that avoids the recovery dots. But on the other hand, if this vertex was infected to begin with, then this vertex is avoiding this vertex. This is because of this blocked arrow. So this remains until this vertex is getting healthy at this point. So as a result, these two infection arrows, this infection arrow is sort of ignored. And because of the ignoring some of the infection arrows, so you get less infection here. So that doesn't mean that the process on an average is monotone or not, but the Harris construction coupling doesn't work. That's a big impediment and challenging this, studying this model. Now we also, that's why we have two different critical values here. We cannot say they are equal. I conjecture that they are, but we don't have a proof yet. So in case of straight line, for fixed alpha positive, we define lambda alpha minus to be the infimum of all lambdas for which you have, for which the infection persists for every positive probability, starting from finite sets. And we define lambda alpha plus to be the critical value below, so that which is the supremum over all alpha, all lambda, for which the process in the infection dies down. Infection, everyone heals with probability 1. So in case of contact process, lambda alpha minus and plus are the same. But in case of this, we cannot say they're same yet because we don't have monotonicity. But they're ordered. Lambda alpha minus is smaller than lambda alpha plus. So the first result that one of the main results that we have shown is that the change in alpha, as a function of alpha, they are linear. They are not. They are bounded by two linear functions. So they're not growing like a square or something. Okay, now, in case of cycle graphs, the same similar results as we have for regular contact processes hold qualitatively, but for this value of lambda c, that if lambda is large compared to linear function of alpha, then we have supercritical behavior that the process survives for exponentially long time. And if lambda is small compared to linear function 1 plus alpha, then the process dies out. So the same constants hold here also, same bounds. But the behavior is the same. Only thing is that the critical value lambda c is moved linearly as a function of alpha. Now, in case of hubs, that was the main reason for the contact process having no critical values in the BBCS paper, Christian's paper, was that the contact process, if you restrict on a hub, it survives for exponentially long time for all positive lambda. So on the contrary, here, as soon as alpha is positive, the survival time in our order boils down to a polynomial survival time. It's very exponential. Not only that, we can compute exactly the exponent depending on lambda and alpha, which would capture the persistence time of the infection. So it's delta, it's in terms of basically an eigenvalue of a certain generator of a contact continuous time Markov chain. So it turns out to be this expression. And it's correct up to little of one correction. So here, in case of hubs, the behavior is drastically different because it drops down from exponential to polynomial as soon as alpha is positive.
Can you repeat what's delta?
So delta is basically 1 over gamma, where gamma is in the next slide it will be clear. Delta is 1 over gamma, where gamma is an eigenvalue of a associated Markov continuous time Markov operator.
Which Markov operator?
Yeah, that will be clear in the next slide in the proofs.
Okay.
I'll describe that.
Okay.
Yeah, just wait. Yeah.
I see.
Yeah.
Would you expect lambda c to be positive if alpha is positive?
That's
a configuration model.
So for the configuration model, our guess is that it will persistence time will be either a polynomial or stretched exponential, but we are not sure which one is true because we don't have monotonicity. That's why we cannot combine the activities of the stars and say we can, because stitching together requires monotonicity argument. That's what is missing yet so far. So, but we, it seems like either of those two will be the case. But definitely it will be less than exponential n, which is the case for regular contact process. Okay, yeah, so that's a question that I have. That what next? That the Shovik that asked. We expect either n to the order of 1 or exponential little of n. Right? If we piece together, but we don't have the one-to-one yet. Also, there are other questions here. We only consider the model where individual interest is to protect him or her from infected friends. But if there are collective decisions or collective societal movements or societal approaches, then that particular models will have different behavior. You don't know that yet. So the difference is that in the individual attempts, you are saving yourself only, You're not telling your friend's friend that that person is infected. But in case of more aware society, you'd expect you'll tell all your other friends of that, or you tell your friend to tell his or her friends that currently that person is infected, so that they can go home temporarily and avoid spreading, etc.
So the avoidance strategy is just avoid that person, but not necessarily to wear a mask when you are around that person. Just stay away from them for a while.
So other strategy can be that if I see my friend is infected, I will say that please go home temporarily. Otherwise, you will spread infections or something like that. Something of that order.
Okay.
Or that also depends on social awareness, how important you feel. Etc. There are different variants from that perspective, but I'm not going to there in this model. But that's something to consider in the future. Okay, so now let me quickly give some the proof ideas. In case of the straight line and the graph, the cycle graph, when lambda is smaller than 1 plus alpha, we manage to bound it by a biased random walk with a negative drift for the rightmost and the leftmost. For the rightmost negative drift, for the leftmost positive drift. There are a lot of technicalities involved, so I'll not go into the details of it, but that's the crux. But there are lots of dependent structure here because of the particular dynamics that is introduced. So that creates lots of dependence, which is unavoidable. So the construction is non-trivial, but I don't want to go into the technicalities here. For the other direction, when lambda is large compared to alpha, then we use some version of the what's called block construction in oriented percolation case. So we divide the space-time into blocks of this form where 4 vertices are there and some time tau. So time tau is such that whatever the configuration is with some infected vertices, eventually we have all infected vertices and all edges active. So if that happens, we call that block good block. So the idea is that if you have a good block, then the infection passes through it to the next level. And we show that if lambda is large compared to a linear function of alpha, then a block is good with high probability, independent of all the interference coming from its neighborhoods, because it's very highly dependent structures because of the interference. And once we establish that, then we can compare with well-known structures, which is called oriented percolation, which sort of has the property that if the oriented percolation has each site has probability p of being open and 1 minus p of being closed. If p is close to 1, then you can have an infinite path using open vertices only. You can compare that with that, and so the infections persists for a long time, forever, in case of infinite graphs. And in case of cycles, the infection persists for exponentially long time because this sort of pushes the infection upward when it sort of shrinks down to small. So that it has a locally positive drift. Yeah, as I said that there are lots of dependence and then that cannot be ignored here. So the bound has to be uniform irrespective of what happens in the outside world. That's why the construction of these blocks are very, very crucial. So, okay, now I come to the star graph and the question of the Markov chain that I promised. So in case of star graph, the behavior is the following, that when the center is infected versus when the center is not infected, there are two different dynamics. when the center is infected, that means when the center is 1, then the leaves, they follow, each of them follow a Markov process, continuous time Markov process with generator given by this, where the states are combinations of 1, 0 and AD. A means active, D means deactive for the edges, that is linked to the hub. And 1, 0 corresponds to the infection status of the vertex. There are 4 possible states then. Infection status, 2 possible values, and the status of the edge, 2 possible values, altogether 4 states. So each leaf, the status of each leaf behave like a Markov, continuous time Markov chain on this 4 state. And when the center is uninfected, healthy, then it there's a uniform way decreasing of the number of infected leaves, but it's not much. It just decreases by order 1, by geometric amount of number. But the time it takes to decrease, it always tries to push infection to the center. So once the center gets infected, it tries to push the infection again for the leaves go increase and so on. So the way the infection, which is different from the contact process, is the following: that because of this Markov behavior, at any time t after, let's say, if the infection phase for the center stays for t amount of time, then at the end of it, you have on an average approximately n times e to the power minus t, e to the power gamma t amount of leaves that are left, where gamma is the largest eigenvalue of the operator, negative of that. So now, if this becomes less than 1, then basically there is no infected leaves at all. So that's the time that so we have to wait till we have a large infection time for the center. So the probability that you have a large infection time for the center is polynomially small. So you have to wait polynomially long amount of time to have a large infection time for the center, and during that, all of the leaves goes down to vanishes, goes down to healthy status. The infection vanishes. So that's why we get polynomial persistence here, as opposed to exponential, where this behavior is absent in the contact. Now, we have done some simulation to show what happens in case of cycle graphs. So this is the alpha axis. This is a heat map, alpha axis, lambda axis. And for each combination of alpha and lambda, we have done independent simulations for, I don't know, for probably 100 times of the process, starting on a cycle of length, let's say n equal to 1,000, I guess. And I looked at the proportion of time of this iteration, proportion of iterations, the process survived for a long time. So we defined long time beforehand, which is between polynomial and exponential, something linear, which is between, logarithmic and exponential. So if the process survives beyond that time, then we have counted that as a success. And then we have plotted the proportion of successes here. So when lambda is small, alpha large, that means most of the cases, the process dies out. This end corresponds to that. And the other end corresponds to the situation where lambda is large, alpha small, then most of the cases, the process doesn't die out. So the boundary is in between, which is like a linear function where things gradually go from black to white, and there are gray regions there. So it seems that it's maybe indeed the lambda is a straight function, of a straight line function of lambda itself. Okay, questions? So that's the end of this portion. Now I go to the next portion. As I said, next portion is exploratory. This is ongoing work with Bud Mishra and Iravamsi Naganti of a student in NYU. This is more like a bird's eye view, and then at the initial stages, outbreak of a pandemic, what kind of aspects can be considered from one perspective. There are, of course, not only one perspective, there are so many different perspectives, but this is just one of them. So when pandemics with a highly contagious disease breaks out, where people are dying because of the strength of the infections, and also there are many people who are carrier without knowing. So there are asymptomatic carriers. Then ideally, we would like to test everyone frequently before letting them out, letting them be out of in the street or interacting with others, going to schools or office or going to shops, etc. But that itself may be very difficult to do, because of different constraints, impediments. Cost is definitely one constraint. People not agreeing, and there are thousands of constraints that can create problem for testing people frequently. So so one possible way to tackle this is that to have sort of a badge system. So depending on, and then doing the testing in a batch, like a pool testing. So the badge, the idea is that once you have a green badge, for example, that's sort of a green light that you are free to move without any restrictions. And you can think about multiple layers of different badges depending on how many access you want to grant. I have in this case just used 3: green, orange, and red. So red meaning that you have your test has been tested positive. So depending on the policy, you can be asked to stay at home for for the time being, or you can have very limited access just to have basic survival needs and so on. That depends on the policy, of course, again. And orange is somewhere in between that we don't know, since we are doing pool testing, so we are not sure whether you're green or red, so somewhere in between, so you have limited access. Now, what are the ways that you can possibly transfer from green to red, orange, and orange to red, and how does it work? So you do this testing in a fixed. So think about the scenarios, particularly in underdeveloped countries where there's not much resources also. So there are some fixed test centers or places where they can do pool testing. So once your pool test is, the pool size is also a parameter. So if you have more resources, you can reduce the pool size even to 1. But if you don't have resources, then you may have to go for higher pool sizes, particularly underdeveloped countries where they have many people, highly populated underdeveloped countries. Pool sizes is there, and then there are a number of pools. When you go to one of the pools, once the pool test is, if the pool test is positive, you keep on having your green status. If your pool test is negative, your status is downgraded to orange, and from orange you will downgrade to red. Now, then people will, and then once you have, of course, red, then you will have restricted movement. So people will come back to test again for the next pool test to see whether they have changed the, because it happened not because of that person, but others participating in the pool test. But
sorry, how do you downgrade from orange to red if you have more people in the pool?
No, if you test positive, if you're originally orange, if you test positive, you can red. But
from green to orange also is positive, right?
Yes. So this you're basically downgrading by 1 level.
Okay, fair enough.
And then once you test negative from both green, orange and red, you go back to green because you have tested negative in the test. But then you can control the rate at which you are testing. So if a person has a green badge, then that person can test more frequently than a person with a red. If you have a red badge, you can ask that you have to come back 2 days after, for example. Not now. You cannot do immediately. You cannot jump again. And then in terms of, so now what happens to what is the difference between the different badge holders? They have limited accesses, so the interactions vary between different. So, okay, so now it sort of gives rise to.
Sorry, yeah. Do we know what color of badges other people have? Like if I have green badge, do I know Christian has red or blue?
No, you don't know others.
So it will not affect how I interact with other people. Like it's not going to tell me who is safer to interact with green?
So it's because of security and privacy reason, it's only your.
You only know your
information only
status.
yours.
Okay, fair enough.
But the pool test is like whoever is arriving, it's like you can think about it as a random collection from the population that is coming to the pool tests, and like before joining a class or going to office. So now this gives rise to 9 compartments instead of 3. So I consider SIR model in this case. So an SIR model, and also there's another thing to consider is the structure of the interaction. So there can be a graph structure, like that's most likely there will be realistically that there are local interactions more, and then as you go far apart, the interactions decreases. But for this simulation study, I just have considered only complete graphs. So there are 9 possible combinations of them. And then there are transitions between them depending on several parameters. So one set of parameters, let me just describe the set of parameters. Yeah.
If I'm recovered, why do you care what badge I have?
No, so it's like you can go, you're going back to your household. You're staying with the household, right? So I don't know who are you staying with there.
But I'm recovered in your SRR model. If you put all the recovered states, if you collapse them, it just will not change your dynamics,
essentially the
right?
dynamics will do that. So it just will not affect the dynamics. Yeah. If you're recovered, it will not happen. Yeah, so the parameters in this case are, so first of all, the state space can be described as D sub B. D is the disease status, B is the batch. So 3 × 3. And then the parameters are the rate at which you are testing. Then the freedom, which is how frequently you are allowed to go, which is a fraction. So, and then beta and gamma are the original parameters of the SIR model. Beta is the infection rate, gamma is the recovery rate. And if a badge, just a green badge will have freedom phi of G, orange badge will have freedom phi of O, and red badge will have freedom phi of R. So these are fractions between 0 and 1. So if you have a fraction, it's a number between 0 and 1 strictly, then it essentially reduces the interaction of that group with others. So for example, if you make it 0, then you are basically establishing quarantine, that you are not allowed to interact at all. You have 0 freedom. And there are other parameters also, like for example, if the test is developed recently, it's not guaranteed to have nice results. It can have false positivity rates, false negativity rates. The pool size is another question that also has to play a role in the overall cost.
Sorry, which parameter is accounting for the specificity, sensitivity of the test, or the efficacy of the test? Which one?
Both of them.
Oh, okay.
Both of them can be there.
Okay, thanks.
And then, there are different roles for them. They're not exchangeable though, because if a test is false negative, that has one role, but if the test is false positive, that sort of amplifies things also, because it sort of means that more people will go into quarantine, and then that can increase the corresponding cost of quarantine. And there can be other parameters from the pool size, etc. So like pool size can also vary depending on the constraints. Size, number of pools can also be there. And also, it can be a closed society where people are not going out mostly, or it can be, like New York City or some big cities where people are sort of constantly rolling in, then the concerns are different. Then the prevalence rate also, may have may be a discontinuous functions also. So these also can be, if we have this pool testing data available at the aggregate level, then we can also estimate the prevalence, disease prevalence. From there, if there's a sudden jump because of some super spreading event or some new strains, etc., that also can be tracked. Okay, so now there are different questions that can be asked. So I have done some simulations here, some indications I haven't done in theory yet. That's to do. So So this is a simulation of the, not a simulation, but if you solve the ODEs numerically, and then I have here 9 figures, I shouldn't have so many, but let me just quickly say what happens. So the left is the all 9 ODEs I'm plotting. The right is the one which is combined S and I and R only. In the first row, I have no restrictions. That means all the testing rates are equal, all the freedoms are equal. In the second row, I'm keeping testing rates equal, but I'm reducing freedom for orange and red. For example, I'm reducing the red freedom to 0. The reds are quarantined. And the third row, I have both reduction of freedom and reduction of testing rates. So overall, it says that if you grow from the upper to the lower levels, the infection is suppressed. So, and then you can control these parameters. You have this phi parameters and the t parameters to make it supercritical also very, also. But of course, it comes with a cost. If you do it like this, then you may end up quarantining many people who are actually not infected. So there's a quarantine cost for that. So now, how much freedom will be there? It's also an interactive parameter. It can be thought about as an interactive parameter. And then depending on the prevalence, you can adjust that if you want to run a scheme.
So if you keep people longer, essentially denying freedom,
yeah,
meaning lockdown for longer.
Exactly. So if you just say that everyone goes to home,
lockdown.
Then sort of it reduces the infection right away, but that is not
Yeah.
sustainable because of the other economic.
But the disease doesn't rebound, right? It stays at 0 basically.
Yeah.
Doesn't come back up again.
Yeah.
Okay.
But you can, the advantage here is these are flexible. This is according to you. Then once you see there is a super spreading event or something that the prevalence has gone up, you can, tighten things for a week or something. You can have restrictions and then you can relax it gradually. So this is like a framework for, doing all these different things. So, but the next thing is that the ODE doesn't answer all the questions. So for example, one of the questions is that since we're doing pool testing, there's always be chances that even if I'm not infected, my test comes false positive, which is I consider to be false positive. I can, be against the authorities who are doing the test, saying that I have no symptoms and nothing, but you're saying that my test is positive. So I'll not agree to this system. So then we need to know what's the average time or expected time to get back the right badge color. So infected gets red, and non-infected gets green badges. So for that, those questions cannot be answered from the OD model. So we have also studied the agent-based version of this model, where individual players are acting according to some Markovian rules also here. And then we computed over different iterations, we computed the average number of time it takes to get the right badge. And we plotted against pool size. So it's yeah.
So normally when I think of agents, I think of these complicated systems where every agent has their own strategies, their move and stuff. Mm-hmm. Isn't this just the stochastic version of your ODE model you're studying here, where you just have each vertex has 9 types and you have some transition rates? And so in principle, for example, I could probably study the birth process, calculate the largest eigenvalue and predict R naught, right? No.
Yeah, so
analytically.
I did it. Yeah, that should match with this probably. But I did it. We did it like we have a bunch of different people in the community, and they are following their rules, what they are supposed to do.
I see. But you're a mathematician, so you could calculate, look at the 9x9 matrix, and try to find the largest eigenvalue.
Yeah, but there
might be difficult.
There are difficulties there because the interactions are highly nonlinear. So that's why whether linearization will be a good idea, I'm not very convinced yet. So because yes, that can.
No, but you can use the next generation operator method to find the eigenvalue. But can you convince me again? Why do you say the ODE system will not allow you to?
The system always goes for the limiting behavior, right? How does it behave in the long run proportions? But I'm asking for an individual person. How much time I have to wait till I get a first right
correct badge? Okay.
Because if that is too long, people will not agree to this.
we should ask our mathematicians here, but wouldn't we expect law of large numbers even for this? So there's ODEs here. It's 9. Okay, there are 9 states instead of 3, but we can still write down a stochastic system. And shouldn't just the general Kunz method just work and give us a law of large numbers? Or maybe your method, if it's non, but your times are exponential, right? So probably it's just standard. Yeah, so, it converges to this ODE, no?
Yeah, the only thing is that the rates actually, they are very highly they involve rational functions and so on and so forth. It's very highly nonlinear. That's why I'm not sure whether that will give the right.
Oh, your rate, can you go back? Why is the rates are nonlinear?
Yeah.
Yeah, no, these are just rates, no? Can you go back to why your rates nonlinear?
So there are, in terms of the parameters, I'm saying, there are different, no. There are other parameters like TG, TF, all these fees are there, then false positivity rates are there, and then pool size is there. So if you consider all of them, this is highly nonlinear rates.
But it's still a linear Markov chain, right? I mean, it's just, it's memoryless, it just has rates. It's just a finite dimensional system with rates. It will have a law of large numbers, and you could even study the behavior of a single person that still is within the methodology of the standard law of large. I mean, it's more or less done by Kunz already, right?
Okay, so I'll take a look at this, whether this question, for example, can be, this question can be answered.
No, so it's more of a comment. So you certainly could, and there is even a way in which you could try to sort of induce this limiting mean field probability measure and then study how it differs from the original system. So there are ways in which you can try to do this.
Okay, so I'll have happy to
certainly
learn.
Possible.
Yeah, I'll be happy to learn because I was a little bit bogged down because of the non-trivial rational function that I'm getting, but I'll be happy to take a look.
Okay. You get your solution tomorrow. Okay, come to the talk tomorrow. Similar.
For a simpler one.
Simpler. The same idea.
Similar idea.
Yeah. So come to the talk tomorrow.
Yeah, sure. I'll be here. So but the other hand, that the pool size increase, if the pool size increases, then the total number of infection reduces. That's probably intuitive, because if you have more pool size, then a lot of people will be asked to quarantine for the time being. But nevertheless, there are, if you look at the cost, from the cost perspective, which strategy is a good strategy in this framework, then good strategies are low cost strategies. That the cost has different components. One is the cost of quarantining people. If you are quarantining people, then of course their work hours are being lost. So you have to compensate you meaning the authorities may have to compensate that persons in some way. So that has a cost itself. So you don't want to quarantine people too much, because that increases the cost. C2 is the other way. On the other hand, the cost due to spreading of the infections. This is health-related costs, fatalities, long sufferings, and etc. And then all of them depends on the particular parameter in this framework. So this can be a function of these things. And there are two other costs, which is the overhead cost, and the other one is for the testing. So if you have more test budgets, you can, as you have seen the morning talks today, that there's a test budget. Depending on that, you have to plan accordingly. And if you have unlimited test budget, then it's a different story. So now if you combine all these costs, and then what we found out in the simulation study, at least, is that initially that the cost is not a monotone function of any of the parameters. So for example, the pool size also, for certain cost structures, the pool size also can, the optimal pool size can also be not 1, but something bigger than 1. Yeah, so now this framework can also be used, as I said, for detecting whether there is a certain surge. And then if you have good idea about this cost, so a huge amount of effort is needed for understanding how much the cost is per person or per capita.
But that's another cost also to overall economy,
Yeah.
supply chain, collapse of
so-
economies. You
yeah.
know, they have this kind of big outbreak of terrible disease.
Then once you have the total cost idea, then you can choose the right parameters and you have the freedom of adjusting them so that your cost is same. Then you may have to have other objectives like optimizing other priorities. Okay, so this is the framework I had. So yeah, thank you.
Excellent, thank you. Excellent presentation. Any questions, any more comments? I know we ask you so many questions, yeah. Okay, so in which case, let's thank Shirshendu one more time. Very nice. And the next talk, Jorge, is it now or 3:30?